Hi, in this video, I'll solve this problem. The very first problem on the first day of the first time the IMO, the International Math Olympiad, was organized. It was given in Romania in 1959 with 7 teams participating. IMO problems are famously hard. For me, for example, when the IMO problems come up each year, some of them I have no idea how to solve. Some others, I may figure out a strategy after thinking about it for a long time. But this problem, I looked at it and I knew right away how to solve it. That makes it an easy problem. Any problem that I can solve right away counts as easy. Wait, what? How can an IMO problem be easy? Well, think about it in the past. When the IMO first came into existence, the organizers probably didn't have a very good idea how good the good math students are. So they may still be trying out different things, feeling out how hard to make a problem. Here's the second problem from the same exam. I would consider this a normal homework or exam problem in a regular algebra class. Another reality is, back then, nobody was studying or training for the IMO because the IMO had not previously existed. It took a particularly interested or passionate or curious math student to learn things outside the regular curriculum, such as number theory and combinatorics. And this is a number theory problem. The first IMO problems only needed to have a little number theory and a little combinatorics, and they already counted as hard. But afterwards, when people started preparing to take the IMO, everyone started learning number theory and combinatorics. The problems needed to get harder and harder. That's why when we look back at old problems, they appeared easy. But that's only because both us as later generation math students and them, the people who selected the problems, have the benefit of hindsight. Let's do this problem now. All right, let's strategize. We are given a fraction, and we need to prove that it's irreducible. A fraction a over b is irreducible if and only if a and b are relatively prime or coprime, meaning the GCD of a and b is equal to 1. So they're asking us to prove that the numerator, 21n plus 4 and 14n plus 3, have GCD of 1. What do we know about GCD? There's this result from number theory. That's directly a consequence of the Euclidean algorithm that says that the equation ax plus by equals to d if and only if d is equal to some multiple of the GCD, where all the letters are integers. A is an integer, x, b, y, d, and k. It says that this combination can be equal to the GCD. And second of all, it says all linear combinations will be some multiple of the GCD. Therefore, in this case, it's sufficient to prove that a times the numerator plus b times the denominator is equal to 1. All I need to do is find an a and a b where this is true. Well, this must be true for all n. If it must be true for all n, then a hint is that on the left side here, the n needs to go away. It needs to cancel out because if there's an n left, it cannot stay constant at equal to 1. The n needs to cancel. Aha, so that means if I expand this out, I have 21an plus 4a plus 14bn plus 3b equals to 1 like this. I need this to be equal to 0, and I need, therefore, the rest of it must be equal to 1. So I have two equations, two unknowns. It's a straightforward system. I can solve this system. I get my A and my B and QED. All right, let's solve them. (21n plus 4 over 14n plus 3 is irreducible if and only if GCD of 21n plus 4 comma 14n plus 3 equals to 1, and that if and only if there exists a b integers such that a times 21n plus 4 plus b times 14n plus 3 equals 1. It is sufficient. I'm pretty sure it's also necessary, but it doesn't matter. It's only sufficient to find AB such that the coefficient of n, which is 21a plus 14b equals 0, and then the constant 4a plus 3b equals 1. Like I said, I'm pretty sure it's also necessary, but it doesn't matter. All we need to do is find the A and B. If we got the A and B, we're done. And this can be solved pretty straightforward using standard techniques. I can eliminate A, for example. I can multiply the first equation by 4 and the second equation by 21, negative 21. 84a plus 56b equals 0. Negative 84a minus 63b was negative 21. I add side by side, these cancel. I got negative 7b is equal to negative 21. That means b is equal to 3. I substitute back into this equation. 4a plus 9 equals 1. 4a equals minus 8. A equals negative 2. Negative 2 times 21n plus 4 plus 3 times 14n plus 3 is equal to negative 42n minus 8 plus 42n plus 9 equals 1. QED. I have found AB such that that linear combination is equal to 1. Therefore, the GCD of the numerator and denominator is equal to 1. I'm done. QED. Hope that's been fun. Click subscribe for more contents. Thanks for watching. Bye.